Okay, so in the last class we discussed about a double integral. Okay, so we define this double integral. Suppose function is defined on the bounded rectangle. Suppose f is a function from some rectangle D to R. So where D is a rectangle is bounded by x is bounded by the interval a and b, and y is bounded by some c and d. Then the volume of the region bounded below by this d, bounded above by this function f, then we define the volume is double integral over d f of x comma y dA. So this is nothing but, if you know the exact limit, they can write integral a to b. This is x limit and this is y range, f of x comma y dy dx. So first dy, because we take here limit of y. Otherwise, if you first you take c to d and then integral a to b, f of x comma y dx dy. Okay, both are equal. So the function is defined on the bounded region, bounded rectangle. So it's an exact rectangle. Suppose it's not a rectangle, some other shape, and we know how to define the double integral, right? So suppose one variable is bounded. Suppose x is bounded by a and b, but this y depends on the function of x. Maybe it's g2 of x, and this is g1 of x, where this g1, g2 are continuous function. G1 and G2 are continuous on the interval a comma b, that the Fibonacci theorem says double integral over the region R, f of x comma y dA is integral a to b integral g1 of x. So first you have to evaluate the integrate contains the variable. So since the variables in terms of x, therefore first you have to integrate with respect to y. So after that you have to integrate with respect to x. So this is a first formula for Fibonacci. Suppose the y is independent of x, then this is the integral value. Suppose, so this is the first one. Suppose y is bounded by some c and d, and x is bounded by some f1 of y. Sorry, don't use f1, h1, and less than or equal to x, less than or equal to some h2 of y, where this h1 and h2 are continuous function on the interval c comma d. Then the integral over the region R, f of x comma y dA is nothing but integral c to d, integral h1y h2y f of x comma y dx dy. This is a limit for x. That's why we read. So this is Fibonacci theorem. Now, suppose it is very difficult to evaluate this inside the first integral. You can interchange. Suppose it's very difficult to evaluate this one, so we can interchange the integration. That means you got to find the limit, a boundary limit for x, and then a variable limit for y. You can change it. Okay. So first you try to evaluate the given one. If it is not possible, then we can go the other possible. So already we discussed one problem. So what is the problem? Sin x, I think sin x by x. Okay. So this problem we discussed. So this problem we discussed, double integral over the region R, sin x by x dA. Okay, if you put R means we got to put dA here. Okay. So it's given that triangle, the sides are x-axis is the bottom of the triangle, and then y equal to x boundary region, and then x equal to 1. So if you look at this region, how it look like? So y equal to x, so it goes like this, but x should be 1, therefore is x equal to 1 line, and x axis. So this is our region R. Okay. Now we know the limit for x. So x varies from 0 to 1. Y varies from this 0 to y, 0 to x. So depends upon this one. So therefore you can find integral this sine x by x dA is nothing but integral 0 to 1, this x limit, and then 0 to x, because y equal to x is varying from 0 to x, is depending upon x, and then sine x dx dy dx. So now first you evaluate this with respect to, integrate this with respect to y, you get 0 to 1 sine x by x into y dx. Okay. Now we can integrate this sine x by x. So and then we got to put upper limit and lower limit for this integration. You got a x, we can cancel x, we'll get just integral 0 to 1 sine x dx. So this is nothing but cos x 0 to 1, we'll get minus cos x, because the integration of sine is minus cos, so we get minus cos 1 plus cos 0 is 1. So it's approximately 0.46. So we will get is answer. But suppose you want to change the limit, then what will happen? So that is, if we change in terms of the limits in terms of x, so y limit is 0 to 1, because we know that x lies between 0 and 1, and we know that y equal to x. Okay, so y equal to x, substitute here, we get y is bounded by 0 to 1. So now we take the first limit is y limit. Now x varies from 0 to y, sin x by x dx dy. Okay, but evaluating this is very hard. Okay, so that's why, so just you try this one. Suppose you are not get the answer, you try this integration. So depending upon, you change the limit. Okay, so you have to there is no general rule for predicting which one is which order of integration is will be good. Okay, but don't worry about this. Start with your integration. Suppose you get the answer, no problem. Suppose your choice does not work, you try to other thing. You change the integration limit. Okay. So these are things we discussed in the last class. Okay, now we define what is area of the boundary region in the plane. So if you take the function f of x comma y equal to 1, and that integration is called the area. Okay, so definition. So what do you say? The area of a closed bounded plane region. If you take the plane region, so what is the plane region? Maybe we can call R, is how we define the area. Capital A equal to, just you take the f of x comma y equal to 1 function, that is constant function, then integral double integral over R, just dA. So this is we define area of a closed region, closed and bounded plane region, or plane region is very important. Okay. Now we discuss some example. So actually we are taking the function f of x comma y equal to 1. Okay. Now, for example, find the area of the region are bounded by the curve y equal to x, the line, and y equal to x square parabola in the first quadrant. In the first quadrant. A into. Okay. So what is the area bounded by this one? So first you you draw the picture, and then you can evaluate. So now the first one curve is y equal to x, therefore should be this. And then another curve is parabola, y equal to x square. So maybe like this. Okay. Now you take the region bounded by these two curves in the first quadrant. Therefore, only this inside portion is our region. So this is our region R. Because bounded by this curve y equal to x and then y equal to x square. So this is bounded by these. So we got to find this area of this plane region because it is contained in some plane, xy plane. Okay. Now clearly, so therefore we have a lower limit is 0. Okay. So maximum, this point touches, what is the point actually? 1, 1. Okay. So if we take this, so this actually point x-axis 1. Therefore, what is the formula for area? So area A is double integral over the region R dA because the function is 1. So therefore, double integral dx. So first you got to write. So x range is 0 to 1. Okay. So the y range is actually, what is the below curve is x square. Below what is the bottom curve is x square. So what is the upper curve is x. Therefore, it varies from x square to x. Okay. And then first dy and then dx. Because the function f of x comma y equal to 1. Now first you integrate with respect to y. We keep this integration. So y lower limit x square to x dx. So this is x minus x square. If we integrate x square by 2 minus x cube by 3 after the integration of x, so 0 to 1. So you'll get 1 by 2 minus 1 by 3. So 1 by 2 minus 1 by 3, you get 1 by 6 cross multiply this. So therefore, area of the region bounded by the curve y equal to x square, y equal to x is 1 by 6. Maybe we can take one more problem to this. So find the region R. Okay. Okay, maybe I can write. Find the area of the region R enclosed by or bounded by. Enclosed by the parabola y equal to x square, and then the line y equal to x plus 2. Now first you got to draw the picture. So one curve is y equal to x square. Okay. So therefore the curve should be, but it's not given that first quadrant or second quadrant anything. So just a parabola. So this curve and y equal to x. So y equal to x means what is the curve look like? If you take, this is 0 point. If you take x equal to 0, substitute here. If you have x equal to 0, y is 2. Therefore, this is a point 2. And suppose if substitute x equal to minus 2, so this is a minus 2 point. If substitute x equal to minus 2 is 0. Therefore, this line passes through these 2 point. These 2 point. Okay, anyway, this graph, they will meet somewhere. So this parabola and then this meet some point. Okay. Now we got to find area of this curve. Okay. So area of this region. Okay. So what is the formula? Area equal to area A equal to double integral over the region R dA. So this is nothing but, now what is the, maybe you can split this integration into maybe two integration, and then you can easily solve it. Okay, so otherwise you can directly write. So now what is the limit for x? So look at this point. So anyway, the curve intersects somewhere, right? So it intersects here. So what is the point here? Okay, and it intersect here. So what is the point here? So we have a x square equal to x plus 2. You got to solve this equation, okay, because both are y. So therefore, if you take x equal to 1, okay, sorry, if you take, okay, x square, I think x equal to 2 will satisfy, because so substitute x equal to 2 square is 4, and that side is 2. So 2 plus 2, 4. So therefore, so this point, in the intersection, this point is x is 2. If x is 2, y is 4. Therefore, this is 2 comma 4. Anyway, the upper limit for x is 2. Now, what is the lower limit? But x should be negative in this case. Okay, so what is the another solution? If you substitute x equal to minus 1, the left hand side is 1, the right hand side is minus 1 plus 2 is 1. So it's satisfied. Therefore, this point is nothing but minus 1. Okay, therefore, the limit for x is minus 1 to plus 2. And then integration, what is the lower curve here? So again, x square. And then what is the upper curve? X plus 2. Therefore, x square to x plus 2 is the range of y into dy dx. Okay. Because what is the lowest curve? This is our curve, lowest curve. This is nothing but y equal to x square. So the upper curve is y equal to x. Sorry, y equal to x plus 2. So therefore, the limit is, lower limit is x square, upper limit is x plus 2. Now, if we integrate and then substitute, we will get integral minus 1 to 2 y, if substitute x square to x plus 2 dx. So this is nothing but x plus 2 minus x square. If you integrate, you get x square by 2 plus 2x minus x cube by 3 minus 1 to 2. If you substitute the upper limit 2, we get 4 by 2, that is 2, and 2 plus 2 is 4, and this 2 cube by 8. Therefore, 8 by 3, this is upper value, minus, if substitute lowercase 1 by 2, so 1 by 2 minus 2 minus minus plus 1 by 3. So you'll get this 6 minus 8 by 3 minus 3 by 2, that is plus 3 by 2 minus 1 by 3. Anyway, if you simplify these, you'll get some 9 by 2. I think so. So because if you sum these two, you get 9 by 3, 3, 3 cancel. So we get 6 plus 3 by 2 minus 9 by 3. So 9 by 3 is nothing but 3. So 3, this is 6, and then minus 3 is 3. So 3 plus 3 by 2. Therefore, this is nothing but 6. And then 6 plus 3 is 9 by 2. So 9 by 2 is the area of this curve. So you can directly solve it. So otherwise, we can split, maybe you can split this integration into two integration. Maybe you can split, we can, this is one region R1 and this is another region R2. We can find the integration, because this is a point somewhere we can choose. Otherwise simply, okay, this point, not to that point. So this point is minus 1 comma 1. You can take this region, small region. Take this region is R1 and this region is R2. We can find the region for area for this region, and then find the area for this one. Anyway, you can directly find the area of this one. Okay. So this is the area of the curve bounded by this thing. Okay. Now, next we define what is average value. So average. So usually we have to divide the area. So the next definition is average value of the function f. So definition for average value. So again, there are function defined over the region R. So simply writing the formula, average value of f over the region R is defined to be 1 by area. 1 by area of the region R into double integral over R f dA. Okay. So you have to divide the area of the R in the double integral, you get the average value of this one. Okay, maybe we can solve one problem to find the average value of the function over the region R. So first you have to find the area, and then you have to find that integral over f separately, and then you have to multiply. So exercise, find the average value of the function f of x comma y is given by x into cos xy, cos of xy. Okay, over the rectangle. Over the rectangle R is defined to be x is bounded by 0 and 1, and y is also bounded by 0 and 1. So we know what is the area. So otherwise you can find the double integral over R f of x comma y dA. So both the limits are given, 0 to 1, 0 to 1. F of x comma y is x into cos xy. You have to integrate with respect to dy first and then dx. So integral 0 to 1. Therefore x is constant. We have to treat x is constant. What is the integration of cos? We have minus sin xy. And then what is that? By x, right? What is the integration of sin ax? Dx?
Yes, by x.
Yeah, by x, because x is constant. So therefore, we have to put the upper limit, lower limit 0 to 1 dx, but we can cancel this x. We can take minus outside. So integration 0 to 1. If such is the upper limit, we get sin x. Sin 0, 0, we get dx. So again, if we integrate sin, integration of cos is plus, right? Sorry, plus sin. Integration of sin only, we have minus cos. So therefore, minus cos x 0 to 1. Oh, sorry. The limit is x limit is 0 to pi. Sorry, but y is 0 to 1. X limit is 0 to pi. Okay, now 0 to pi. Now this is equal to minus cos pi is minus 1. Cos 0 is 1. So therefore we have 2. So because minus 2 plus 2. So 2 is the value of this, but we need average value. So first we have to find, and then we have to find the area. So what is the area? Area of R, the region, is double integral over R just dA. So it's nothing but integral 0 to pi, integral 0 to 1 dy dx. So if we integrate, we get y. If substitute upper limit, lower limit, we get just 1. Therefore, we get just dx. And this is nothing but just pi. Okay. So therefore, 2 into 1 by pi, that is 2 by pi. Therefore, average of f over R is 2 by pi. because area is pi. That's it. Now, we have some other thing. We have to change the Cartesian coordinate into polar coordinate. Sometimes it's very difficult to integrate if you keep x and y. So if you change x and y in terms of r and theta, we can easily evaluate the integration. So that is double integrals in polar form. Double integral in polar form. So you have to substitute x equal to r cos theta, y equal to r sin theta, and the integration we have to in terms of r and theta. So maybe I can so given function is f of x comma y is given. It has some limit, okay? So you have to substitute x equal to r cos theta, y equal to r sin theta. So the given function convert into a function, new function is a function of r and theta. Okay, or you can take f of r comma theta. It's not an issue. We can simply same thing. And then we have a integral. So simply I can write. So similarly, the limits also will change. Okay, suppose the limits for x is something, some a to b, and then y is the limit something. Then here we have a limit for r and theta. Okay, so r is some limit, and theta is some limit. So since theta is an angle, therefore should be radians, or 2 pi, or 0, or pi, and so on. So I simply write that formula by new version of Leibniz theorem. So double integral over r f of r comma theta dA is nothing but integral theta varies from some alpha to beta, and this r is a function of theta. Suppose r is some function of g1 theta and r from g to theta. Function f of r comma theta, but not dr d theta. We have to multiply r dr d theta. Okay, so replace dy dx by r dr d theta. Okay, so that is the thing. So why this formula is came, maybe we will discuss a general formula later. Now we solve some problem to this. So similarly here, what is the area in polar coordinates? Okay, everything in the polar coordinates. So what is the area? So area A is defined to be double integral over R. So in the previous case, we just take dA, where dA is nothing but dy dx, but here R into dr d theta. Okay, so that is the area in the polar coordinates. And then similarly, we define what is the average is nothing but 1 by area into that integral, double integral over r f of x comma y, all the things you know. Okay. Maybe we solve some problem to this. How to change the given function x comma y to polar coordinates. So exercise. Find the sometimes find the polar moments in the interior. So they will ask some other thing. Okay, maybe simply I can write. So anyway, the function is given by x square plus y square. Okay, f of x comma y equal to x square plus y square. Okay, sorry, I think not the function. Okay, anyway, we solve some another function, another problem. So evaluate integral So evaluate double integral over R e power x square plus y square into dy dx, where R is the semicircle. R is the semicircle bounded by x-axis. Bounded by x-axis, and the curve y equal to square root of 1 minus x square. So actually y, what is this? Just to square both sides, we get just the x square plus y square equal to 1. Okay. So this is same as y equal to square root of 1 minus x square. So this is a region. Now if you draw this region, at least a unit circle. So that is bounded by one curve is unit circle, but it should be semicircle. Therefore, from minus to 1 to this one, and then take the x-axis. So this is our region R. Okay. Okay, I think it takes. Okay, take the same thing, same length. Okay. So this is one. So this is a region R. Now you have to substitute x equal to R. So what is the radius here? Actually, our radius is 1. So anyway, if you take x equal to R cos theta and y equal to R sin theta, okay, then clearly the x square plus y square should be R square, because cos square theta plus sin square theta is 1. Therefore, x square plus y square is R square. Now the integration becomes, now we change everything into thing. Now what is the angle? So this is the angle. So what is the angle? 0, from the 0 to pi. What is the radius? Is 1. Okay. So the theta value from 0 to pi limit, the radius value is 0 to 1, because the unit circle radius is 1. Okay. Into e power x square plus y square is nothing but R square, e power R square, into the general one is R dr d theta. Okay. Now we change of variable, so we can how to integrate this one. So we call this R square equal to some t. Now therefore we differentiate 2 times both side 2 times R dr equal to dt. So if you take R equal to 0, then t is 0. If R is 1, t is 1. Therefore limit will not change. So therefore integral 0 to 1, sorry, 0 to pi, integral 0 to 1, simply we can write e power t, because we are substituting R square is t. And this dr into dr can be written as dt by 2. Therefore dt into d theta by 2. So we can easily integrate. So therefore integral, I can take 1 by 2 outside, 0 to pi. Integration of e power t is e power t. If you substitute upper limit, therefore you get e power 1 is e minus e power 0 is 1 into d theta. Again, e minus 1 is a constant, and then if you integrate these, we get theta. If substitute upper limit to lower limit, we get pi. Therefore totally we get pi by 2 times e minus 1. So this is the value of the region. Okay, so domain anyway, the area or volume bounded below by this semicircle, bounded above by the function f of x equal to e power x square plus y square. So it's very difficult to evaluate directly. Therefore, you have to change into the polar form, and then we can easily integrate. Okay. So that's the thing. So similarly, maybe if we take some other function, take f of x comma y equal to 1, simple function. Next exercise. F of x comma y, we take 1. the function bounded by the circle x square plus y square equal to 1, but in the first quadrant. That means quarter circle. Quarter circle means what? 1/4 of the circle, but is in the first quadrant. So maybe you can write the quarter circle of quarter circle x square plus y square equal to 1 in the first quadrant. Okay, now what is the thing? What is the area? Sorry, what is the volume? So therefore, you have to draw the picture. So it's a circle, unit circle, but should be in the first quadrant. Therefore, the graph should be like this. Only the quarter circle of this first quadrant. This is 1, and this also 1. This is 0. Okay, now what is the, actually this is a thing. We know the radius should be, anyway, you got to substitute x equal to r cos theta, y equal to r sin theta. Now, what is that angle theta? So this is the angle from 0 to, this is pi by 2. Okay, so therefore double integral over r, actually this f is a 1, therefore this is nothing but r dr d theta equal to integral, double integral. What is the limit for theta? Theta varies from 0 angle to pi by 2 angle. And what is the radius? Radius is always 0 to 1. Okay, what is r? So from this we get a relation that x square plus y square equal to r square, right? Now what is this? We can write x, because already r is there, right? So you can write x square plus y square into dr d theta, because already r is there, that's why, otherwise you got to write thing. So therefore we'll get just we got to adjust that r to this, we get x square plus y square. Correct or not? Yeah, no, maybe, sorry, we can read it again. So what is r from there? So I think
R square dr.
no, I think
dt.
the function itself. Sorry, tell me again.
Here R square is equal to 1, no, sir.
Yeah, because the radius is 1. Yeah, so therefore what you'll get?
So we can directly write dr d theta, or
Okay, I think okay, the function is 1. If you write r dr d theta, you say. Okay.
Sir, whether the answer is pi by 4?
No, answer is actually pi by 8. So actually, what is given that r square into r dr d theta. Actually, the function itself is actually x square plus y square. That's a thing. So it's not actually x plus y. The function itself, because 1 equal to, we know that, right? Because 1 is nothing but x square plus y square. So if it is 1, anyway it's 1, but 1 can be written as x square plus y square. Therefore, it's nothing but r square. Therefore, this is nothing but r square into r. There's nothing but r cube. So therefore, 0 to pi by 2. If you integrate r cube, we get r power 4 by 4. The upper and the lower is 0 to 1 d theta. So it's get 1 by 4, you can take outside. And then if you integrate a d theta, we get theta, we get pi by 2. You get pi by 8. Okay. So the function is anyway 1, but 1 is nothing but x square plus y square. and then we can write this r power 4. Okay, so this is, you got to change the Cartesian coordinate into polar coordinates, and then you can easily find the value. So far we discussed a double integral. So similarly, we can extend this concept into triple integral. So that is, if we take some subset D of R3 and then we define some function. So suppose if we take let some D, which is a subset of R3, and the function f defined from D to R, so is defined to be maybe it's a function of 3 variable. Therefore, the input is x, y, z. It goes to some real number. Maybe we call some w. Okay. Now, if suppose D is again bounded below, the region bounded below by this D, bounded above by the curve f, what is the volume of this one? So same thing. So if we define the same Sn equal to, instead of two function, so we define Sn equal to summation I equal to 1 to n. The function, maybe you can use capital F. Okay, don't confuse with this small f, because we already use small f for two variable. So we use capital F for third variable. So xi comma yi comma zi, we have to pick some point in that small region, and then the area of this small region delta A. Or we can use volume here. So we can take some V instead of V, we can take some VA, capital VA. So volume of this bottom, the small thing. But it's very difficult to visualize the graph. But anyway, you can extend the definition from 2 variable to 3 variable. And then if you increase the number of points in both x and y and z, we will get, we cover more areas. So that is, if you take limit n goes to infinity Sn, that is a triple integral. So limit n goes to infinity Sn. If you take more number of points, then is nothing but we defined triple integral over the region D f of x, y, z, dz, dy, dx. First, we have to integrate with respect to z, and then we integrate to y, and then finally x. Or simply we can say dv. Okay, this is triple integral over f, triple integral of f over d. So similarly, the same property. Suppose you have two functions f and g, the sum of triple integral is nothing but triple integral sum. So sum of separating. So maybe we can simply write triple integral of f plus g over the domain D into dv is triple integral f over d dv plus triple integral g dv d. So if you take multiply with some scalar, triple integral of k times f dv over d is nothing but k times triple integral f dv over the domain D. Similarly, for subtraction also, so maybe I can write here plus or minus this equal to plus or minus this. And suppose f is positive, the capital F is non-negative on the domain D, then triple integral also positive over the domain D. And then the fourth one is, suppose there are two functions f and g, but f is bigger than or equal to g in the domain D, then triple integral over f dv greater than or equal to triple integral over triple integral of g d over the same domain. So all the properties we discussed in. So similarly, suppose this d, suppose we can write a union of two things, designed union of two in says d1, d2, then we can split it. So but that is triple integral over d f dv is triple integral over d1 f dv. We can extend anything. So the triple integral d2 f dv and so on. Triple integral over some dn f dv, where d is the union of d1 union d2 union etc union dn. But if you take any two da's, the intersection is empty. So dA intersection GA should be empty set. So if D can be expressed a union of disjoint sets, then we can split the integration. Okay. So the same thing. Now similarly we define the volume. So in the two variable we define the area. So how we'll define? You take the f of x comma y is 1. So here if you take f of x comma y comma z equal to 1, that the integral is we defined to be volume of the boundary region. So definition. So the volume of a closed boundary region. Closed boundary region D. D in space, not in plane, okay, is defined to be V is nothing but triple integral dV over the domain D. So here we take the function f of x comma y comma z is 1. So there is a volume. Okay. So maybe we can discuss some problem and then we can. Okay, exercise. So anyway, here you have to find the limits for x. So similarly, we define average also. Okay. So once we define volume, we define the average value of f. Okay. Anyway, we solve the problem. Find the volume of the region D. Find the volume of the region D enclosed by the surface surfaces. So actually curve means two-dimensional case we call curve, three-dimensional graph is called surface. Okay. Therefore z equal to x square plus 3y square, and the another surface is z equal to 8 minus x square minus y square. So therefore you have to take the function is 1, f of x comma y comma z is 1. Now what is the volume? So volume formula is triple integral over d dv. So first you have to just write what is the limit for x, limit for y, limit for z. So similarly the general case of the what is the theorem that called Fibonacci theorem. Okay. So first the limit of x should be constant. Okay. Maybe I can write here. So actually we have to reduce into, so the limit of x should be some constant. Okay. So therefore x equal to some constant a to b. But the limit of y should be function of x. Therefore some g1 of x and then g2 of x. That is a y limit. But the z limit is function of f5. Suppose some h1 of x comma y and then z equal to h2 of x comma y in terms of x and y. And then first you got to integrate with respect to z and then y and then x. So that's it. So first you got to find the limit for x and then y and then z. That is the idea. Okay. Now it is given that this is z and this is z. You got to simplify. You will get a value for z. So therefore we get a equate this to surface. We get x square plus 3y square equal to 8 minus x square minus y square. So if you take everything one side, you'll get 2x square plus 4y square equal to 8. we can cancel 2. We'll get x square plus 2y square equal to 4. Anyway, this is a ellipse, right? We can divide by 4. We can read it as x square by 4 plus y square by 2 equal to 1. So this will look like x square by a square plus y square by b square equal to 1. This is the ellipse. Here a is 2, b is square root of 2, because a square is 4, b square is 2. So the intersection of these two surfaces is a ellipse. Okay, that is keep in mind. Now, what is the upper boundary of this curve, and what is the lower boundary of this curve? Anyway, the intersection is we get a ellipse. Okay, now if you consider the first equation, okay, what is the x square plus 2y square equal to 4? We will get this one, right? So intersection curve. So from this we can find y. So therefore x square plus 2y square equal to 4. Therefore 2y square equal to 4 minus x square. Therefore y square equal to 4 minus x square by 2. Therefore y equal to, if we take square root, plus or minus square root of 4 minus x square by 2. Okay. Now we found the limit for y. Okay, because plus square root of 4 minus x square by 2 to minus square, sorry, from minus to plus. Okay, now we found that double integral, okay, sorry, integral x integral integral y limit in the z limit. But z is the curve varies from one curve to another curve. It's a function of xy, right? So if you draw the curve, x square plus y square is bottom, but x minus 8 minus x square plus y square is in the outside bigger. So therefore, the range for z is x square plus that what is the curve 3y square. And the upper limit is 8 minus x square minus y square. Now the limit for y is, we get this thing, 2 thing, minus square root of 4 minus x square by 2. I think the square inside square root, okay? We can put the bracket here. And then plus square root of 4 minus x square by 2. So this is the upper limit for y. Now what is the value for x? So this everything should be real number. So look at y. So inside the square root, what is this x? This 4x square, 4 minus x square should be positive, because if it is negative, you'll get a complex number. Okay. So therefore, x maximum. So therefore, x square is greater than or equal to 0. Therefore, 4 greater than or equal to x square. Therefore, what is the value for this x? Maximum to minimum minus 2. Then only if you take square, we'll get 4, right? So therefore, the limit of x is minus 2 to plus 2 into dz, dy, dz. Now just to evaluate, you'll get it. So I hope everyone understand how to find the limit. So first is the given curve you take as a limit for z, and then you have to intersect these two curves, that is solve these two, you get a equation. From this you can find a y in terms of x, and then from that equation y you can find the value of x, range of x. So therefore,
limit, how did you say that?
It's a given curve, bottom, it's a two curve, two surfaces.
Okay.
So this therefore this
Anything can be lower limit and upper limit, sir. Not like that.
Yeah, we can compare these two. Okay, suppose we have to compare which one is smaller, which one is bigger. You take some value, x equal to 0 or y equal to 0. Now substitute here, what you'll get, z equal to 0. But here you will get z equal to 8. Therefore, anyway, this curve is bigger curve. Or if you take x equal to 1, y equal to 1, you can compare the value. Okay. You'll get, suppose if you take x equal to 1, y equal to 1. So here we get 4. But here you'll get, I think maximum you'll get 1 minus 1 is 6. So anyway, this is bigger than this. But maximum we can go x value is 2. Maximum the y value is square root of this one. So you can take, suppose x equal to 100, y equal to 200, it will not work. That's why I'm saying the limit for x. So maximum the limit is minus 2 plus 2. If you give any values of x lies between here, the z values always, this x square plus y square is smaller than 8 minus x square minus y square. So this limits depends on x limit as well as y limit. Okay, anyway, so if you integrate this, minus 2 plus 2, integral minus square root of 4 minus x square by 2, and then plus square root of 4 minus x square by 2 dz. If you integrate dz, we get z. The upper limit minus lower limit is 8 minus x square minus y square is the upper limit, minus x square minus 3y square is the lower limit, into dy dx. So we can simplify, and then so this is equal to integral minus 2 plus 2 minus square root of 4 minus x square by 2, and then plus square root of 4 minus x square by 2. If you simplify, this is 8 minus 2x square, and then minus 4y square into dy dx. Now integrate with respect to y, and then substitute the limit. So integral minus 2 to 2, 8y minus 2x square y minus 4y cube by 3 with respect to y, right? And then you got to substitute square root of 4 minus x square by 2. Upper limit is square root of 4 minus x square by 2, and this is minus into dx. So substitute y equal to this value. So what you'll get? This is equal to integral minus 2 plus 2, 8 times the upper limit, that is square root of 4 minus x square by 2 minus 2x square times, again we have to take this value, square root of 4 minus x square by 2 minus 4 times this one. So y cube already square, therefore we can write actually 4 times 4 minus x square by 2 power 3 by 2, because already the square root is 1 by 2, here power is 3, therefore 3 by 2 by 3. So this is for upper limit, minus, if you sum the lower limit, you will get the same thing. Okay, so therefore you got same thing but minus of this one. So therefore you'll get minus inside, but here we have minus 8 square root of 4 minus x square by 2, and here already minus plus, we will get 2x square root of 4 minus x square by 2, because we have to substitute minus square root of this one. Okay, keep in. So here y cube is again, if you take minus, we get a plus 4 times again 4 minus x square power 3 by 2 into dx finally. Now if you multiply minus inside, maybe you can put plus. So therefore this is plus, therefore 2 times 8. Okay, and then we can take common from these 2 is square root of 4 minus x square by 2, and then this 2 term also. Okay, so you'll get the same thing. So if you multiply minus, this is plus and this is minus, so same thing you will get, right? So therefore if we adjust this and then take this 4 minus x square by 2, square root of 4 minus x square by 2 is outside, therefore integral minus 2 plus 2, 8 2 times 8 minus 2x square times this term, square root of 4 minus x square by 2. Okay, and then the remaining things here, this is actually 4 by 3, this is also 3, sorry. So if you simplify this, you will get minus 2 times this, therefore 2 times this one is nothing but 8 times. So therefore 8 by 3, 4 minus x square by 2 power 3 by 2. So that's it, into dx. Now you have to integrate. So maybe I can write the direct answer. So if you simplify this, you will get 4 times square root of 2 by 3 if you take some outside. Okay, so what are things if possible you can take outside from this one? Integral minus 2 to 2 4 minus x square power 3 by 2 into dx. Because you can take 2 from this 8 minus 2x square. Okay, therefore you'll get 4 minus x square power 1, but here power is 1 by 2, therefore add 3 by 2, 4 minus 3 by 2. Okay, so therefore but here root 2 is missing for this term, therefore multiply and divide by the root 2, so we can adjust, we will get these things. So once you get this closed form, we can easily simplify. So we'll get final answer is 8 pi into root 2. What is this pi actually? This is actually called to some error function. Okay, so it's very difficult to, okay, not error function. Okay, if you solve this one is very difficult. So therefore, we got to substitute the thing x equal to 2 times sine u. 2 substitution of variable. If you find this one, we can easily evaluate this integration. Okay, because 1 minus x square can be written as cos square x, and then we can cancel the square and we get cos cube, and then you can easily integrate it. Okay, substitute x equal to 2 sine u or some sine t something, so you will get this one. So answer is 8 pi times root 2. So this is a method to find the volume of the surface, volume of the region bounded by the surface, these two curves. Okay, so now define what is the average of the function in the space. So if you know all the variables are bounded by some constant, then you can easily integrate. Z is bounded by some a1 to b1, y is variable from a2 to b2, and x is varies from a3 to b3. You can directly integrate. Okay, that is bounded surfaces. If you know all are constant, we can easily evaluate. Otherwise, we can use this. So the next definition is for average of the function, average value. So same thing, average value of the function f over the region D is nothing but 1 by the volume of D, because in the 2 dimension we call volume, triple integral f times dv over the domain. So this is the average value of this. So same thing we discussed in the last class, previous thing. So almost we covered this thing. Okay, so the problems are we will discuss in that. So similarly here also, so maybe I can say how this it will work. Okay, so here we can change. So in the second function of 2 variable, we can change the Cartesian coordinate to polar coordinates. Here you have to change the Cartesian coordinate to cylindrical coordinates. For 3-dimensional, we have a cylindrical coordinates. So what is the substitution here? We have to take x equal to what is that thing? Usually you take x equal to r sine theta something, right? So you have to apply that one. So cylindrical coordinates. Okay, so maybe in the next class there is something how to change this one. Is we have to change. You can use the Jacobian thing. Maybe I state that one definition, and then we can stop the class. So what do you mean by Jacobian of 2 function? Okay, we have 2 function, u and thing. So definition. Suppose we have a 2 transformation, x equal to as a function of u and v. Again, y also some function of u and v. Okay. Now, what is the Jacobian of this 2 function u and v? You can just denote j of u comma v is nothing but the matrix determinant of the matrix. You have to differentiate this x with respect to u x is nothing but g actually. So and then we have to differentiate x with respect to v, and then we have to differentiate y with respect to u, and then we have to differentiate with respect to v. Okay, this is actually called Jacobian determinant or Jacobian. The j is called actually Jacobian. Jacobian determinant. So actually this is nothing but simply, so what is x is nothing but g. So you have to differentiate g with respect to u partially. Again, we have to differentiate g with respect to v, and then we have to differentiate h with respect to v partially, u partially, and then differentiate h with respect to v partially. Using this, suppose if we change that is actually you have to transform the, actually you have to change the transformation. So given equation is x and u and v, we have to change in x and y, then we got to use. Otherwise, given x and y, you have to change u and v, you can use the Jacobian. Okay, so simply we can denote this determinant is Jacobian of, we have to differentiate this x and y by this u and v. We have to change it. Or g by h, g comma h. Either you can use the notation because we can x is nothing but g, y is nothing but h. In this case, we are taking. So therefore, the double integral over r f of x comma y dy dx is nothing but you have to change the variable. So therefore, f of what is x is a new function g. Okay. So therefore, g of u comma v comma h of u comma v times modulus of the Jacobian value. So the determinant Jacobian u comma v into du dv. So over the new region D. Okay. So sometimes it's very difficult to solve this region. We can transform the region into another region. Okay. So maybe sometimes in the region, in the plane, maybe I can say this. Suppose one region is here. Suppose this is a region R. Okay. So we can transform. So finding the area of the same as, suppose you are shifting this region into somewhere same, look at the same picture, but the position is changed. Suppose I change the position of this region into somewhere. So therefore, finding the region of this is same as the finding of the region of this, because both have same picture, same area. The only thing is the position is changing. So this transformation, we got to change the coordinates. So okay, so here x equal to 0, 0, but you change the center is somewhere here. So you have to change the coordinates. So same thing here, we have to change the Cartesian coordinates into polar coordinates. Okay. So in that case, what is the transformation? We have x equal to r cos theta. The polar coordinate, we have to x equal to r cos theta. It's a function of r and theta. Instead of u and v, we have this thing. So therefore, y equal to r sin theta. So therefore, this is nothing but the function of r and theta, and this y is nothing but function of r and theta. Now, what is the Jacobian of this r and theta? Is nothing but we have to differentiate this with respect to r first. So therefore, you have to keep cos theta is constant. Therefore, you have to fix cos theta, and then we have to differentiate x with respect to theta. Therefore, minus r, derivative of cos is sin. Therefore, minus sin theta. Now we got to differentiate the y with respect to r. Therefore, we get sin theta is fixed constant. Differentiation of r is 1. Now fix r, differentiate sin, we get cos. Therefore, r cos theta. So the determinant of this. So what is the determinant of this? R cos square theta minus plus r square sin theta, r sin theta. We can take r outside. Therefore, we get cos square theta plus sin square theta. That is 1. Therefore, we get r. So if you substitute here, what you'll get? Therefore, we already proved that double integral over r f of x comma y dx or dy dx is nothing but integral over maybe the new region f of what is x? Function of r and theta. Okay. So therefore, simply we can write r cos theta because x is r cos theta, y is r sin theta, into what is the Jacob, because the formula have the Jacobian, modulus of the Jacobian. Here Jacobian is r. Therefore, r. What is du? But here u is nothing but r. Therefore, dr d theta. Okay, so you can change any coordinate to any other function. Okay. So you got to choose the suitable function. Maybe we can solve one problem quickly and then we can stop. So related to this. Maybe I give the idea to solve the problem. Suppose exercise, solve 0 to 4 integral x equal to y by 2 to y by 2 plus 1. So this is the value for a thing. So the function is 2x minus y by 2 dx dy. Anyway, we can directly we can integrate, but anyway you can apply the transformation. So what is the transformation we are going to use? So choose this function is u. So u is the given function 2x minus y by 2. And then we can choose that the limit y by 2. So we can just try. So after this substitution, what you'll get? So what is x and what is y? So from this, what is y? Y is 2 times v. Let's say cross multiply 2, you get y, this one. Okay. Now, what is x? So if you sum these two, because this is nothing but x plus x minus y by 2. If you sum these two, y by 2 cancel, we get x equal to u plus v. Okay. So therefore, we get a relation. So therefore, what is the transformation? We get, and then what is the Jacobian of uv? We have to differentiate u with respect to x. So this is u. If you expect to with respect to x, you will get 1 because y is treated as a constant. And then the second one is we got to differentiate u with respect to y. We get a minus 1 by 2. Sorry, actually, you have to write the formula. What is actually dou x by dou u, dou x by dou v, and then dou y by dou u, dou y by dou v determinant. So this is nothing but x is nothing but this. If you differentiate with respect to u, we get 1. With respect to v, we get 1. And then this is a y, there is no u, therefore 0. Differentiate with respect to v, we get 2. So what is the determinant? You get 2. Jacobian is 2. Therefore, the given integration becomes, so integral 0 to 4, integral y by 2 to y by 2 plus 1, that function 2x minus y by 2 into dy dx or dx dy equal to, now actually this is a range, a value for x and this is value for y. So therefore, what is the value for v now? So v varies from, so since y equal to 2 times v, if substitute y equal to 0, therefore v is 0, therefore starting from 0. But if substitute the maximum value is y is 4, therefore if substitute y equal to 4, therefore v equal to 2. Therefore v varies from 0 to 2. Now what is the limit for u? So we know that this thing. Okay, so therefore we'll get what we'll get 0 to 1, maximum 0 to 1, because if substitute this y by 2 is nothing but v. So we know that x equal to u plus v. So if is given that the limit for x is, the lower limit is x by y by 2, but we know that v is nothing but y by 2. So y by 2 cancel. Therefore u is 0. The starting point is u is 0. Now what is the maximum value? So the maximum x value is y by 2 plus 1. This is the x value, but x is nothing but u plus v, but v is nothing but y by 2. We can cancel again y by 2. Therefore u is maximum 1. And what is this inside function? Is just u. And what is dx? So from this we can differentiate this with respect to x, what you'll get? You just get du thing. So therefore, by the definition, this is into Jacobian into du dv by the formula. So therefore, the just integrate Jacobian values 2. We can take 2 outside and then integrate with respect to u and then integrate with respect to v. So therefore, 2 integral 0 to 2 u, that is u square by 2, 0 to 1 dv. So you get 1 by 2. Again, if we take 1 by 2 outside and 2 to cancel, we get a v. If we integrate v, we get a integrate dv is v, and then 2 minus 0 is 2. Okay, so this is the. So this formula is very useful if we change the transformation position. For that, you need a Jacobian. Okay. Okay, anyway, we can stop now. Similarly, for 3 variables also, instead of 2 variable, because suppose 3 variable, the Jacobian is, we have to differentiate 3 times. So dou x by dou, we have to change 3 variables. Jacobian of u, v, w. It's nothing but first you have to differentiate x with respect to partially with respect to u, and then x with respect to v, and then x with respect to w. So on so on, y, and then finally z. Determinant of this. Same thing. Okay. Okay, anyway, I can stop now. In the next class, we discuss some problems. Okay, bye.